So in this video, we're going to talk about water levels, displacement, and buoyancy. And it all starts with Archimedes' Principle. And Archimedes' Principle states that an object submerged in a fluid experiences an upward buoyant force that is equal to the weight of the fluid displaced. And that buoyant force, otherwise known as the buoyancy, determines whether an object floats, sinks, or remains suspended. And the buoyancy depends on the relationship between the object's weight and the buoyant force. So first, let's take a closer look at Archimedes' Principle in action. This is a classic experiment, and this is still used in some fashion today. So here in the left image, we have a weight that is suspended above the water, and that water is held in a tank. Now, just above the water line, we have an opening in the tank, such that if the water level increases, water will begin to flow out of the tank and fill this bowl. And that's exactly what we see happen in this right portion of the image. The weight is lowered into the water, it will displace some water, raise the water level, and water will begin to leave the tank and enter this bowl. Now we can see that in this example, 3 kilograms of water has been displaced, which means the buoyant force is equivalent to 3 kilograms. Now also, being this object is fully submerged, the volume of water displaced is equal to the volume of this object. Now we can also look at the example of something like a tennis ball floating or being partially submerged in water. So again, it's the buoyancy that determines whether an object floats, sinks, or remains suspended. So we'll talk more about this shortly, but it depends on the combination between the weight and the buoyant force. And you can see in this example, the buoyant force is larger than the weight. So we will have this object float. Only a small portion will actually be submerged. So let's talk about all of this in a little bit more detail. Let's take a closer look at displacement and buoyancy. So again, an object displaces fluid equal to its volume when that object is submerged. And the buoyancy depends on the weight of the displaced fluid. So there's 3 possible outcomes. We can have floating, sinking, and the third case is when the object remains suspended. So let's talk about them in more detail, one at a time, starting with floating. So for an object to float, its weight must be less than the weight of the displaced fluid. So that's what we see in this middle case here. We see that the weight is less than the buoyant force. So that means this object will float. We have a larger buoyant force, which is going to see the object above the waterline, or mostly above the waterline. Then we have the opposite case, which is sinking. So an object sinks if its weight is greater than the weight of the displaced fluid. And that's what we see in this example here. The weight is greater than the buoyant force, so therefore the object will be brought submerged under the water to the bottom of the container because the buoyant force is less than that weight. And then that final case is that of suspension. So we've talked about when the weight is greater or smaller, but what about when the weight is equal? Well, when the weight is equal to the buoyant force, then it will remain suspended. Nothing is driving it up or down or keeping it up or down. It simply remains suspended at the position where the weight is equal to the buoyant force. So let's talk about some of the real-world applications of all of this. Probably the first, most important, and most obvious is that of ship buoyancy. Because ships float by displacing enough water to create a buoyant force equal to their weight. So this portion of the ship that is underwater is not some sort of fortunate accident. It's explicitly engineered into a ship's design. The whole point is the ship must float, and it does so by having this portion submerged, displacing water, and creating a buoyant force. So there's this push-pull effect where water pressure is pushing up, and then we have the weight of the water pulling down. Now, a second interesting real-world application is that of liquid volume measurements. So as we said, displacement is used to measure the volume of irregularly shaped objects. We can submerge an object in water, and the volume of displaced water is equal to the volume of the object. So if we have some sort of simple object here, like a cube, Well, there's no need to do this. We can simply take some quick measurements and perform a simple calculation to determine the volume. But what about a shape that looks more like this? Some irregular shape where there's not some well-established formula and easy measurements to take. In this case, we can use liquid volume measurements to determine the volume. And the way this works is this object would be submerged in water in a container with graduated lines, in a sense that we can see what the water level is and how the volume changes. So if this object is submerged in water, it will displace water equal to its volume, and we can see that change through incrementation on the container. Now, then we have another ship-based example, which is that of submarines, where submarines adjust their buoyancy directly by controlling water intake in what's called ballast tanks. Now, essentially, they are modulating the buoyant force. They are taking more water in and letting more water out in order to go up and down, to sink or float. So in a ship, we sort of have a static scenario. They're not modulating anything. It is what it is, so as the ship is designed. But submarines are designed to actually modulate this themselves, and that way they can sink or float more or less according to their needs. And these are only 3 of many other applications, with some other common examples being hot air balloons, hydrometers, floating bridges, and certainly so much more. So as always, let's summarize some of the most important information from this lesson. First of all, we started with Archimedes' Principle, which says that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid displaced. Now, the buoyant force is known as the buoyancy, which determines whether an object sinks, floats, or remains suspended. And the buoyancy depends on the relationship between the object's weight and the buoyant force. Now, we then took a closer look at displacement and buoyancy to analyze these relationships in more detail. And we said that an object displaces fluid that's equal to its volume when submerged. And the buoyancy depends on the weight of the displaced fluid. So if there's a larger weight of fluid displaced, well, then the buoyancy will be greater, and vice versa. So in specifically talking about the 3 potential outcomes, we have floating, sinking, and suspension. And in floating, an object floats if its weight is less than that of the weight of the displaced fluid, as we just discussed. Sinking is the opposite case, where an object sinks when its weight is greater than that of the displaced fluid. And then lastly, we have suspension. And that's when an object remains in place, suspended in place, if its weight is equal to the weight of a displaced fluid.